Hello everyone and welcome to the next session of Digital Days. My name is Silas and I will moderate this webinar. The topic of today is efficient HF signal transport over SMA connectors. Our speaker today is Ramco van de Griendt, who is working as a field application engineer at Würth Elektronik ISOs. Before we start with the webinar, I would like to point out one thing. You will be muted during the webinar. This means that you cannot ask us questions via your microphone. But you have the chance to ask your questions anytime via the Q&A tool. You can find us this below on the right side. Today's webinar will be about 30 minutes long. After that, we will answer your questions in a short Q&A session. If we are unable to answer all your questions within this time, we will answer them via email after the session. Last information for you, you will all receive the recording and the presentation of this Digital Days session today. And now I wish you an exciting and interesting webinar. Thank you.
Many thanks, Silas. For me, good morning to you all at the side of your cameras. What Silas already told, my name is Ramco van de Griendt, a field application engineer for the electromechanical parts within Würth Elektronik. And today I want to talk with you about the HF transport or HF signal transport over the SMA connectors. This is the agenda of this session. I think everybody can read that because EM wave and that sort of things. I will go back directly and because of the time directly into it. First, some small introduction. What is EM wave and losses and that sort of things, so we can go ahead on that way. First, the insertion loss. How is insertion loss? How the S21 parameters? How is that build up on that way? First, radiation losses. As you can see below, the radiation losses are more into the going from the connector out of it and radiated to the environment on that way. The reflection losses are here in that area where the connector meets the signal trace on that way. So you get there because of your soldering there and that sort of things, and your tin and changement of the geometry and that sort of things. You get reflections, and that you get reflection losses. Then absorption losses. Absorption losses are here in the whole area of the PCB, if you look into this drawing. And that's because the FF4 material or the material of your PCB absorbs some energy and you get there some losses. And then you get the Joule losses. The Joule losses are also over the whole area of your signal trace, and that's because there, of course, you have copper. Copper makes losses, and that losses are there on that way. That's nothing we can change there. That's the way of the nature, because the copper has big losses. This all makes that you have the insertion losses. If we measure the throughput on that way from the S21, and that's from the inside, you are going to that way on from port 1 to port 2. That's the total losses you see there with the radiation losses, reflection losses, absorption losses, and Joule losses. And that's the total what you can do. And that all things we must take in consideration on that way. And of course, there also you have reflection losses and radiation losses in the total way, and that's what you see. Then the impedance and resistance. If you're looking to the DC current, then you have, of course, working with resistance and no impedance on that way. I think everybody knows the Ohm's law, so that's no problem. Then if we look into AC current, and that's with 50 hertz or something like that, like we taking out of our current net and that sort of things, you see there that we have losses like impedance, and you see also the calculation. That's also mentioned, of course, in ohm. With high frequency, you get a characteristic impedance on that way. You must take in consideration the electric field and the magnetic field. And there you must have a look on that way, and that's how you're going to be. Of course, the magnetic field is around the conductor, and the electric field is spreading out of the conductor. And that ratio on that way, you get the characteristic impedance on that way. Then you have also permeability. Permeability is also, if we look into our passive components, a lot of things we are using there. If we look into air or ceramic, then the magnetic field is traveling besides the conductor. Like you see here, this is the conductor. And then you have the electric field, of course, what I said about the characteristic impedance. But if you have permeability, then you have also, you're changing your magnetic field lines on that way. And then you must take in consideration the vacuum permeability and the relative permeability, like you see later on, what will be there, the value on for different sort of materials. And you have also the permittivity, and also I come back later on. I'll come back into the relative permeability. You see here some values. Air, for instance, is around 1, water and plastic also, and vacuum also, copper also. But if you look into, well, for instance, iron powder has a different permeability, and then you make that take in consideration how you can calculate the characteristic impedance. The permittivity, you see here, the permittivity is also a relation again with the characteristic impedance. Permittivity is a little bit different. It's not the fully magnetic field. It more absorbs the electrical field and really absorbs. That's the absorption, what I already told in the total losses you have in your PCB on that way. Permittivity, you have also the permittivity 0, that's for vacuum, and the dielectric relative permittivity you see here. Vacuum, air, PTFE, for instance. PTFE is a most common used material in a coax cable, for instance, has pretty a low permittivity if you're looking to different ways, like an everform material for your PCB. That's the everform material is twice so high in that way. So that's the things what you make in consideration, because every changement of your permittivity, changing your characteristic impedance, change of your characteristic impedance means that you have higher reflection losses or absorption losses or something like that. So that's what you must take in consideration. That's some sort of material on that way. Trace impedance. Trace impedance, you see here, a trace is built up with like an inductor, a resistance, a capacitance between the trace and, for instance, the ground plane as a reference ground plane, and admittance. With that, you see this, you can calculate also the characteristic impedance. But of course, the frequency is counting really high on that way. If you are really low frequency or 0 in frequency, only the resistance and the admittance are going to be there, and normally the admittance is that low that your characteristic impedance is only the resistance of the trace on your PCB. Do we in an infinite frequency on that way, then you see really that your characteristic impedance is only taking of the inductor value, the inductance value, and the capacitance value. And that's what you see here. So the inductance and capacitance value are from influence there. So that's what you need to also take in consideration. So that's why how you can calculate everything on that way. I come back later on how you can play a little bit with that sort of values or with the distances between everything, so you can go ahead. Again, here you see the capacitance value, the permittivity for vacuum, the relative permittivity, for instance, for everform material, what we saw is 4.5. You have the surface and the distance between the ground plane and the trace on that way. That's how you can calculate this, the capacitance. Of course, here also you can surface the width multiplied by the length. Of course, if you look into the inductance value, you can calculate it on this way. I not mention every formula, it's only let you see how you can calculate it for your future designs in that way. Again, if we look into that, LC, characteristic impedance, divided by the C or square root of that, you get the characteristic impedance. And how you can play a little bit with different ways of microstrips and grounded coplanar. A microstrip, for instance, is used very much as an antenna feeding line on that way. Sometimes, of course, with a grounded coplanar like you see here, but you see here that you can play with the width of the microstrip, and if you are raise the value of the width, you decrease the characteristic impedance of your line. That's what you also can see, of course, here in this formula. If you are increasing the permittivity, the relative permittivity, also decreasing the characteristic impedance of the line. Changing the gap between those two, if you are using a grounded coplanar, I come back later on what will be the benefit of that, is that you're here increasing it, that you're also increasing your impedance on that way, and that's because you are changing the capacitance there, and the capacitance there is for influence there. So that's what you are doing. So if you are increasing this gap, you are decreasing the capacitance, and you are thus increasing the characteristic impedance. And it's also with the height or the distance between the top layer and the ground layer. On that way, you're also using and changing it there. Back to S parameters. Again, what we already told, reflection, the reflection, that sort of things. You have the S21, and that's mentioning it. You first put a signal into the first port 1, and you take the output of port 2. That's what you are measuring, the S21 parameters. On that way, how it's going to work, and that's are the insertion losses. If you have a reflection on that way, you are only measuring the S11 on that way, and that's only what you're doing is checking it in a power domain. And of course, this is because of the power, you have here the logarithm on that way how you can calculate. If you have, for instance, you are losing the half of the power on that way, you have a minus 3 dB, and that's signal power, so you have the half of the power. So that minus 3 dB is for a lot of applications not the right way to handle. And you can calculate it, of course, on this way, on that way. And of course, if you are calculating it in dB, then 30 dBm minus 3 dB is 27 dBm on that way. So then you really can easily calculate it on a good way. Then you have VSWR. VSWR is the relation in the voltage domain, and you are calculating there the voltage standing wave ratio. And that's because of the reflection you have on the first port on this way. So the voltage, the sinus wave is not going fully through to the output. So you have reflection here. And this changement will measure it here. You have the Vmax, that's your input, that's your output, and that in between here, the Vmax and V minus, you have the ratio of the VSWR. And if you take that in consideration, then you really can see on a good way how you can do that. Another way to calculate or to measure how good your signal and how good your trace impedance is to measure everything in a TDR measurement or time domain reflectometry. You are sending out a pulse into the device on the test of the dot, and you get some reflections back. And that's over the amplitude, but also over the time. And you really can see there, if you put there a VNA measurement on that way, that you really can see on which level or which distance you really can see where the change of your characteristic impedance is there. Later on, I can let you see with real measurements we did with some PCBs how that looks like. Here you see some, for instance, how it looks on that way. You have here normally a 50 ohm trace impedance, what is really normal for an SMA connector. You see really here big discontinuities, and this one is really changement in the geometry of the connector, for instance, and then you see it's going to be stabilized. And this could be that here you're going from the coax cable to the connector itself, also here above, and then you see it's going to be leveled. Maybe there's some soldering. That's, for instance, again, because I don't know really the measurements about this, because the real measurements I did later on. And you read this over the time, and really can see here how many it's going to be. Typical layer setup. You have a 2-layer setup, of course. At the top, you have a layer setup. If you're looking to there, about a ground opener, RF on top, ground on the bottom side. If you are going to 4 layers or higher, then you have RF on top, some pre-pack in the middle, then a ground plane again. Then you have, if you have a 4-layer core inside, and then a ground layer again, then you have the rest of the PCB. That could be a setup how you can do it. The last one, of course, the second layer is really low production cost, but it's really hard to do because you could have some problems there with interferences and that sort of things with the rest on top of it. So that's why if you have really a bigger amount of digital analog signals, also signals like RF signals, then normally a minimum of 4 layers will be used there. So you really can separate the RF layer on that way. It's better for RF designs, have a better ground plane, and dielectric is different there because you have different heights of your same prepacks and cores. Again, microstrip, mostly for feeding antennas and that sort of things, has not really a ground on the RF layer. Normally you see here an RF layer on like you see here. That's more for guiding the signal over the transmission line and not spreading into the PCB. So that's what you need to take in consideration. Radiation, waveguide losses. Microstrip have the middle losses on that way. You really can see here that the electrical field, the red lines are going outside, and the magnetic fields are going to be on that way. So you have no coupling on there. So only here you see that you have at the bottom side, because of the ground layer, it's more stay there and not going to be outside. If we do a ground opener on that way, you see that here the electrical field is coupling into the ground part of the ground opener. And if you are using via also as a sort of via fence, you also have a low impedance coupling to the ground player. So you really have a good one. Then you really can couple everything on an electrical field into the PCB. So it's not going to spread out. So less interference like that, lower EMI problems maybe for the future. So that's a good one. Still, you can see, of course, here the magnetic field. Then if you're looking to transport of coax signals, coaxial cables, for instance, has low losses because everything is surrounded by a shield normally, and the conductor here, everything, the magnetic field and the electrical field will stay into the cable itself, and that's why you get lower losses on that way. But of course, you need to transport your RF signal over the PCB, and then the grounded coplanar could be a good one. Then you have here a connector with, for instance, an end launch version. And that end launch version, you have here really, you see here a big a pin on that way. It's really a big amount of metal, of brass for this case. Would there be a high or low losses? That's what we're going to deep more in that way. If we're looking first a microstrip and a ground opener, you really can see here that with this simulation that everything is spreading really on a broad way in that way, and with the ground opener you really can see that it will stay more into the PCB. That's really what you can see here. So that's really a good one. Another thing, tips and tricks I can give you with is if you are using solder resist, what normally is really used, you increase his losses there because you're adding there a permittivity. So you're adding there a dielectric, and a changement of dielectric, what I already mentioned to you, it was changement of the dielectric change in your losses. So you get higher losses, a change of your characteristic impedance. And that's what you always can say, take that in consideration. So the best what we can say is there, remove the solder resist from the RF line. And if you are using ground and copen, also from the ground line on that way. So that's really an easy way to do and not really the most expensive way to do. I already mentioned the via fence. The via fence is meaning that you're with ground copen that you are making a low impedance coupling between the top layer of the ground and the low layer of the ground. And that's what you see here on that way. And that reduce coupling on the way of different ways of analog and digital signals of your PCB. Less losses there, so because you have a stabilized ground plane. And you really can see on the right that really the most amount of your electrical field stays in between and not going outside. It's not going to travel over your PCB. That's what you want. A rule of thumb about that via center distance, if you look into that, it's around the wavelength. It is depending on your frequency you want to transmit on that way. So you get the wavelength, so the lambda divided by 10. Then you have the distance of that, how you can do that. And I think everybody knows how to calculate the lambda. Then the combination of the connector and the PCB. If we look into copen waveguide, you have the solder pads, of course, a good ground connection. What you see also here, what we mostly say, okay, if you make sure that nothing is going to travel, it's also okay that you put here at the bottom side of the connector itself a ground plane and make that everything's without solder resist, that you really can solder also fully around the surface of the connector itself. That's why you get a better one. Also to this one, you have a line tapering, and that's you are changing here the distance between the ground plane and the transmission line and the pin itself. Because this is a big, I already told a big amount of brass on that, in this case, of this connector, you get there a capacitive influences, parasitic influences there. And the capacitive parasitic influences could have there a big change of your characteristic impedance, and you get there, could have a big problem of losses. And if you want to reduce losses, you can make sure that you are using that line tapering. You can calculate it on that way with all the formulas I already mentioned in the earlier stage of this presentation. If the losses are still too big at the end, you also add the ground plane of the RF way. You also can make sure that you also are using their take away the ground plane on that way, because of the distance between the top layer and the ground layer on that way, if the distance is pretty too low, that could be that you have also there a capacitive parasitic influences there, and that's what we want to decrease. And then we say you can use a defective ground structure to make sure that the capacitive mismatch will be there, not again there on that way. Now we get more into the practical way. We designed some PCBs, what you already saw, with two sides, a connector on that way, and with looking for the S21 parameters, how that is going to be built up. And of course, on the top side, on the input side, the reflection. This is really how we straight trace with the via fence on that way, with smaller vias, what everybody normally take in consideration, with no tin soldered on the ground way. So there's no, I must say it, there could be a lot of traveling into it, so a higher losses there because of the traveling of your PCB, of a higher reflection and losses and that sort of things. And you really can see here on that way that you are up to 800 megahertz or something like that. You could already have some problems, because normally we are saying with minus 20 dB in most applications, will be okay. For the lower frequencies, if you're going to there from the 6 to 7 gigahertz, you're also with minus 15 dB, it's normally okay. So with already here, it's a stipping, and here with a little bit lower than the 1.2 gigahertz, then you really see that there is a big problem there. So that's what you don't want to have. Also, if you look into the S21 measurements on that way, you really can see that it's with -1 dB, it mostly is okay. If you're looking to back, -1 dB will say that you're around something around the 19% of your transport of your signal in power domain will be okay. So that's also not for the really high frequency. So in this case, if you are using this one, I think for 434 megahertz, it will be okay, for instance. But if you're going to be more above, then you really have a problem. So not for Wi-Fi, Bluetooth, and that sort of things. Of course, if you're using external antennas and that sort of things, because that's what you see with SMA connectors. If we are looking to the TDR measurement, you really can see a big dip. Normally, if you're saying if you are between the 54 and the 46 impedance, that will be for mostly the variation will be okay there, and then in between you must have there. If I go to be a little bit more, sorry, it was too quick. If you look into this one, here first you have the coaxial cable, then you see the first connection to the PC, to the connector itself, then you really have a big dip, and that's already on the way how everything is going to be traveled because you have no grounding planes there. And then you see here all the first connection, and you go over to the PCB. And normally you must here have a straight line like the coaxial cable, and with this one you really don't see, you have a really big variation in impedance, and that's why you see it back on that way. This is the second connector. You say, okay, but that's really strange because the peaks are not that high, because you're already losing some power over the trace, of course. And the first time, that's why you have less power at the end, and that's why you see there different ways of changing. So that's the first one. If we are going to make sure that you're making the line tapering, if you look into here, they have a ground shape, it's going to be travel, and you're going to be downwards on that way. Then you already see that it's going to be better in the lower frequency. Again, the big problem will be erasing somewhere between the 2 and 3 gigahertz. Also, you're seeing here that it's already pretty better. And not only changing of the ground of the ground layer is there, but we also have here the tin added on that way. So we have more ground connection on the bottom side. So you are not traveling a lot of electrical field through the PCB. That's what you see here. So this is already a better solution on that way. TDR measurement, you see the first already the capacitive here problems are a little less. You still have some inductive problems here, and the rest here you see really a big difference. You have here really a 50 ohm impedance on that way. Then this change of layer here, you have really one that's changing, not really a big variation to here, but really a smaller variation. And then you really can see it's up to the 12, 13 gigahertz. You really can dive in, and you also see here on the S21 that not a big EMI problem is there anymore. So that's really a good one, and that's why your transport of your signal for higher frequencies is more guaranteed there. TDR measurement, you see here that it's not fully between the limits, but it's pretty okay. Then the last one I did here, and I checked here, is that you see here on the below side that besides that same shape we had here, we had also here on the bottom side the defective ground structure. So try to reduce there the capacitive mismatch. And because this is a 1.55 millimeter, it could be that it's not be that big differences that you see also here. The change is not really big, only you see here that it's a little bit better between the limits. And that's what you saw in this case. If you have if you have a smaller distance between the top and the bottom layer, this could have a bigger influences there. So you see that there will be a lot of things there to change, and with a high performance connector you also can make it really horrible to transport signals if you don't consider all the changes in your PCB layout. So I hope this gives you more insight. This presentation normally will be also shared with you. So I hope you will get some more information. You can use this also in your practical work on that way. So Silas,
Yeah.
I hope everybody have a lot of questions for me.
Thank you, Remco, for the interesting presentation. Now we will come to the short Q&A session to your questions. So, first question: what stack up of the PCB did you choose? You were talking about influence of PCB and their layout. Will housings also affect the signal integrity?
Yes, of course, the PCB is one thing to consider. Of course, also changements of your housing can make differences. For instance, if you are using a plastic housing, there could be, of course, some interference come into your PCB layout and could have some big influences there. If you are using, for instance, a metal housing where you make sure that your cage of Faraday is really good calculated, then there will be less influences there. So a lot of things to think about besides PCB layout. So that's right. And of course, also use of PCB material will also be a case there. For this case, we are using FF4 material. If you are using, for instance, Roger, that's a more ceramic-based PCB material. It could have some influences. We tested it also. But for this frequency, it's not that big influences. So that's why we put this not into the presentation.
Thank you. Next question. Hi, why isn't the signal pin of the connector soldered beginning from the edge of the PCB, where the pins pad starts on the first picture especially? You have here the mismatch of the impedance.
I have a look on that way.
Of Kidder, the bridge made by the pin.
I think this person is meaning if you look into this way, yeah, it's not fully to the edge. If you look into the bottom side, there's what we already going to the edge of to make sure that the grounding is okay. What we did here in this case, of course, you can still fine tuning this solution. What we did here, in this case, we are not saying. We are also covering the copper to the end of the PCB because that's a much more expensive way, and with this more less expensive way, you already can make a lot of big differences there. I think if we are using that way and we're going more to the copper to the end of the PCB, I'm also really make sure that everything is soldered. Then you really get more bigger influences. But if you're looking already to this one around 50 gigahertz, it's already for a lot of applications and our customer way already a good way to handle this signals. So that's why.
Okay, I think one last question. Besides changes on the PCB layout, will choice of PCB material also affect the signal integrity?
Yeah, the signal integrity, what I already told, if you are using, for instance, a Roger material, you already get differences there into how the epsilon error is changing. For instance, I already let you see it's for 4.5 FF4 material to up to 3.5 for Rogers out of my head. That's changing your permittivity, so that changes also the way of how the losses will be there, especially absorption losses there, so you get better signal integrity. Again, for this, in this way, how we set it up, it was not a big difference. That's why we did not take it with us in this presentation. But if you need to fine tune, you really must go for an 80 gigahertz like this connector can use. Then it could be really a good way. But again, 18 gigahertz is not that used that much in our industry. But again, we could go in contact with that customer if he wants to have more details.
Okay, thank you. So now we are finished with the session of Digital Redays. Thank you, Remco, for your time, for the interesting presentation. Thank you very much all for the attention, and I hope you enjoyed it. See you in the next, hopefully we see you in the next session of Digital Days. Have a good day and bye-bye.
Also from my side, thank you. Bye.